In this video, I will explain to you how the law of conservation of mechanical energy can be applied in solving kinematics and dynamics problems, which are usually done using Newton's laws of motion. So, stick around and get yourselves energized.
Okay lang ba yan? Joke lang ma'am, joke lang. Tubig lang po.
The first problem: a roller coaster starts from rest at a point 45 meters above the bottom of a deep. Okay, you can look at the figure. Neglect friction. What will be the speed of the roller coaster at the top of the next slope, which is 30 meters above the bottom of the deep? We'll let g equals 9.8 meters per second squared. So these are the given quantities. For our first vertical distance, y1 equals 45 meters. That is the distance from the top of the dip, okay, labeled here point A, up to the reference level, which is the bottom of the dip. Okay, the second vertical distance is y2, which is equal to 30 meters. All right. So at the top of dip letter A or point A, the roller coaster starts with zero initial speed. That means it is starting from rest. Okay. So the the roller coaster path, all right. In other words, this curve path is considered frictionless. Okay, and stated that the roller coaster will be able to move up to the second slope represented here by point B, and is asking for the final speed of the roller coaster exactly at point B. So the principle that we are going to apply in this problem, of course, is the law of conservation of mechanical energy, okay, which says that the total energy of the roller coaster at point A is just equal to the total mechanical energy of the roller coaster at point B. And this may be expressed, all right, for the total mechanical energy at point A, the roller coaster, since it's starting from rest, in other words, it has no initial kinetic energy. Okay, the only energy that it has at that point is gravitational potential energy, which is equal to mgy, where y is the height from point A or from the reference level up to point A. Now, when the roller coaster moves downward and rises up to point B, okay, what happens is, as the roller coaster is descending or moving down from point A up to the bottom, it's actually decreasing its potential energy. Okay, it's decreasing potential energy, but it is gaining kinetic energy. In fact, when it reaches this point at the bottom, it's considered to have the greatest kinetic energy. All right, because it is at this point that the speed of the roller coaster becomes the greatest, okay, speed. And so therefore, since it has a large amount of kinetic energy at this point, practically all the gravitational potential energy that the roller coaster possessed when it was at point A will all become kinetic energy at the bottom. And so therefore, since there is no friction considered the amount of kinetic energy is sufficient for the roller coaster to be able to rise, okay, up to the second slope and reaches point B. So that is the way the transformation of energy takes place. At point A, all it has, the roller coaster has gravitational potential energy, no kinetic energy. And then, as it goes down, this potential energy will start to decrease. All right? Every amount of potential energy that is decreased from the original actually becomes the gain in kinetic energy. And so, because of this maximum kinetic energy that it acquires upon reaching the bottom, we say that the roller coaster possesses the ability to be able to rise and reach point B. Alright? So we are asked to find what is the instantaneous speed of the roller coaster as soon as it reaches point B. Okay? Now, the other part of the equation that we are going to use, of course, is to determine what is the total mechanical energy of the roller coaster when it already reaches point B. So we label it here as the sum of the two forms of mechanical energy. Okay, because of its speed v2, all right, we say that it has kinetic energy 1/2 mv squared, and then because it still has a vertical distance from the bottom, which is our reference, equal to 30 meters, it also has a corresponding potential energy, mgy. So if we add this two, we say that that is the total mechanical energy that the roller coaster possesses, okay, when it reaches point B, and that is to be equated later on, okay, to the initial mechanical energy of the roller coaster, which is mgy1. Alright, so this is how we're going to proceed with our solution. We said that the total mechanical energy of the roller coaster at point A must be equal to the total mechanical energy of the roller coaster when it is at point B. Alright, that is the meaning of this conservation law equation. And we can express the potential energy of the roller coaster when it was at point A as the product of its mass times acceleration due to gravity and the distance y sub 1. Alright? And then on the right side of the equation is the total mechanical energy of the roller coaster when it is at point B, which is the sum of its kinetic energy, alright, 1/2 mv squared, where v sub 2 is our unknown variable. Okay, and then we have also the potential energy it acquires when it is at point B because it has a 30-meter distance from the reference point. This is considered here the reference point. So, and you will notice that each term in the equation has uh, the variable mass. And so therefore, we just cancel them out. All right. In other words, there is no need to know the mass of the roller coaster in order to find the velocity or the speed it acquires when it reaches point B. That seems that the mass of the body that is being considered is in fact immaterial. So, as we proceed, okay, since you are looking for V sub 2, we need to transfer gy2 to the other side of the equation, all right? So it's like you subtract mgy2 minus mgy2. And then on the other side, that's supposed to be gy1 minus gy2. All right? We don't have the mass anymore. We just canceled it. And so, um, proper simplification will give us the equivalent formula in finding the speed v2. That is, v2 must be equal to the square root of 2g quantity y sub 1 minus y sub 2. Alright, and when we substitute the given quantities, we will get square root of 2 times 9.8 and to be multiplied to 45 minus 30 this meters, right? And eventually, what we will get is the value for V2, which is 70 meters per second. Right. So we just computed for the unknown variable, okay, and we did it simply by using the formula for the law of conservation of mechanical energy. All right, for our second problem, a well-greased, essentially frictionless metal ball has the shape of a hemisphere of radius 0.150 meters. Okay, you place a pat of butter of mass 5 times raised to the negative 3 kilograms at the rim of the bowl and let it slide to the bottom of the bowl. What is the speed of the pat of butter when it reaches the bottom of the bowl? So we have here a sketch of that bowl. Okay, when you say hemisphere, it's exactly half of the whole circle, all right? So that whatever is the radius of the sphere, okay, can be represented here as the distance from that point, all right, point A, labeled point A, up to the bottom of the bowl, which we also identify the line connecting this point here up to point B. Okay, the radius here is the vertical distance. Okay, we are not referring to the actual path length, okay, from point A to point B. Okay, the path of butter, when released from point A, will of course be moving along the side, all right, along the side of the bowl. But that distance traveled by the path of butter is not what you're going to consider, okay, in determining the speed of the path of butter when it reaches the bottom of the bowl. It must be the vertical height, okay, the vertical height that separates the two points, the rim of the bowl and the bottom of the bowl, and that is labeled here as R, which happens to be also the radius of the bowl. So that is our second problem. Let's look at the solution in the next slide. Okay, so this is how we're going to solve this problem. We know that the radius of the bowl is given R equals 0.150 meters. The mass of the pat of butter also is given 5 raised to the negative 3 kilograms. Since the pat of butter will be placed at point A, all right, so initially its speed is 0, all right. Now we have to take a reference here, and we choose the line, the last line here, okay, which is labeled also as point B. Okay, the horizontal line will be our reference, okay, in defining uh, potential or gravitational potential energy. All right. So again, our principle of the law of conservation of mechanical energy is what we are going to apply here, and that is written in this equation. The total energy of the paddle butter when still at point A is represented here by E sub TA, and that must be equal to the total mechanical energy of the paddle butter when it reaches point B. Okay, so again, what happens is as the paddle butter starts to slide, okay, to slide along this side of the bowl, it's considered to be frictionless. Okay, we can say that its gravitational potential energy that it has originally will be converted into kinetic energy. All right, since from state of rest it's going to be gaining speed. All right, the speed therefore here is increasing until it reaches point B. So at point B, it has the maximum what do you call speed, and therefore it also has the maximum kinetic energy at point B. But this kinetic energy that it acquires at point B is just actually, all right, the amount of potential energy, gravitational potential energy that it has at point A. So we talk about what we call transformation of potential energy, gravitational potential energy, into kinetic energy, and that is what we are applying in this situation, right? So moving on, we now express the potential energy of the bat or pat of butter as mgr, where of course m is the mass of the pat of butter times the acceleration due to gravity, and r here of course is the vertical, all right, the vertical distance that separates point A and the reference. Our reference is indicated by the horizontal line, which we may also indicate as point B. All right, now that's all it has. All right, only gravitational potential energy at the start when it is at point A. It has no kinetic energy yet. All right, but this whole amount of potential energy of the paddle butter will now be equated. All right, to the maximum kinetic energy of the paddle butter when it reaches point B. Hence, we have there equals 1 half mv2 squared, where v sub 2 is the final speed of the paddle butter, and that is what you're also looking for. All right. So, to make it easier, we can cancel the mass m. All right. And that leaves us only with gr equals 1 half v2 squared. All right. And we can isolate v sub 2. All right. And eventually come up with this working formula for v sub 2 equals square root of 2 times g times r. And substituting the given quantities, okay, we have square root of 2 times 9.8 times 0.150. And our answer would be 1.71 meters per second. So that is the speed that we are looking for. All right, we did it using the law of conservation of mechanical energy. Now, what does this suggest? Why do you think the mass, okay, that we canceled from this equation, what does that imply about using the law of conservation of mechanical energy? All right, it simply means that the mass of the body, all right, which actually was given, it's not really that important. Okay, it seems that it is immaterial because in the process of our computation, we were able to cancel it out. So even if the mass of the body is unknown or not given, you can still get the correct answer. Okay, if you're finding the speed, the final speed of the body that is sliding, sliding from point A to point B in a frictionless uh, path, such as this. All you need to have is the vertical distance r. All right. You don't need the what do you call the forces. that must be acting on the path of butter as it moves or slides across this uh, curved path, which usually is what is considered, okay, when you are applying the concept of Newton's law of motion, the second law, and so on. All right, but that's quite difficult to comprehend. I don't know if you were able to uh, understand it or even solve a problem such as like this using the Newton's first law. But I know the Newton's first law is also very powerful tool, okay, in solving problems like this. But now we have an alternative method of doing this problem to make it easier, all right, and less cumbersome. So we'll proceed to another problem in the next slide. This is our last problem. We have a system of two pink buckets connected by a lightweight rope and is released from rest with a 12-kilogram bucket 2 meters above the floor. Use the principle of conservation of energy to find the speed with which this bucket strikes the floor. So as usual, ignore the friction and the mass of the pulley. Okay, as you can see in the illustration, the two masses are connected by a rope, and then this rope is sort of it is hanging around this pulley, a fixed pulley, and we assume that the pulley doesn't exert any force of friction on the rope. Neither are we considering the mass of the pulley. So, in other words, our bucket system is only composed of the two buckets, the 4 kilogram and the 12 kilogram buckets. Okay, any outside force except gravity, all right, any outside force except gravity will be disregarded. All right, so according to the question, we are going to find the final speed of the 12 kilogram bucket, no, as soon as it hits the floor. All right, and in this problem, again, we have to define a reference level. And the floor, of course, is the most appropriate choice to be our reference level. Okay, so in other words, we will be uh, considering the gravitational potential energy of each body in reference to the chosen level, which is the ground or the floor. Now, what or how does the law of conservation of mechanical energy describes, all right, the potential as well as the kinetic energy of the two masses? It says here, all right, that at point A, okay, at point A, which is 2 meters above the floor, it says that the total, all right, the energy total of the bucket system, okay, must be equal to the energy total of the bucket system when the 12 kilogram is about to hit the floor at point B. And that is expressed in terms of this equation. All right, this is very important. This is the foundation of your, what do you call this, your solution. All right. And usually this is the part where students make mistake, how they express, all right, each uh, potential energy and kinetic energy of the two bodies in reference to our chosen level. Now, what do you mean by Mi or M1 times G times Y? This is the potential energy of body A, I mean of the 2 kilogram mass. All right? Since at the start, it is 2 meters above the reference. All right? So the y here, the variable y here, is actually equal to 2 meters. Since it is initially at rest, it has no kinetic energy. All right? Now, what about the 4 kilogram body, which is still exactly at the reference level? Okay? It is also at rest initially, so it has no kinetic energy. The 12 kilogram body has no kinetic energy to begin with. All right? But when the 12 kilogram is just about to hit point B, okay, why does that happen? It's because we imagine the 12 kilogram to be pulled by the force of gravity equivalent to its weight. All right? Now, it's not only the force of gravity that is acting on the 12 kilogram mass, but the tension of the rope as well is pulling it up. All right? The tension force exerted on the 12 kilogram body is uh, somewhat opposing the force of gravity. All right? And therefore, this tension force, you can imagine that this tension force is just the same tension force that's also acting on the 4 kilogram mass. So this is the case where we have what we call action-reaction pair of forces. Okay? The 12 kilogram is exerting a pulling force on the 4 kilogram mass. All right? And that is the reason why the 4 kilogram mass will also be moving up since it's also tied to the other end of the rope. Okay? So what causes the 4 kilogram to also accelerate upward? It's because of the net force exerted on the 4 kilogram mass. The net force consisting of the upward force of the tension and its own weight. That's how we analyze this situation when we are on Newton's second law of motion, if you remember. All right? But here, we are not going to apply the principle of Newton's second law and third law, but we have an alternative way of solving this problem using the principle of conservation of mechanical energy. So, we will be expecting, wait, let me explain first what we have in the right side of the equation, all right? So, it says here that the potential energy of the 12 kilogram block, all right, is equal to what is M2GY. M2GY is also the potential energy of the smaller mass per kilogram as soon as it reaches this point, all right, uh, 2 meters from the floor as well. The moment the 12 kilogram is about to hit the floor, that's exactly what's happening to the 4 kilogram mass is that it's also being raised, all right, because it's attached to the same rope. So it will be raised or lifted, okay, by the rope to a distance equal to 2 meters as well. So that's why at that point when 4 kilogram body is 2 meters away from the floor, all right, it has its own potential energy, and that is expressed as M2GY, where the Y is also equal to 2 meters. All right. Now, what is the other term? What does it represent? It represents the kinetic energy of the two bodies. Hence, their masses is labeled here as M12. All right, M12 is the mass of the two buckets because we treat them as a system. All right, or you can put it this way: when the 12 kilogram mass is about to hit the floor, it has acquired its own kinetic energy. All right, because it will have a, a speed, okay, a maximum speed as a result of the pull of its own gravity, I mean its own weight, causing it to acquire a very high speed. Because of that, it will have a kinetic energy. All right. But at the same time, at that instant when the 12 kilogram is about to hit the floor, the 4 kilogram is also accelerating upward. All right. It starts from zero, then it accelerates equally. That's the key concept. whatever is the acceleration of the 12 kilogram while it is moving down, all right, will also be the acceleration of the 4 kilogram mass, but it is moving up. And when it reaches that instant, this point here equal to 2 meters per second, we can imagine that the 4 kilogram also has acquired its own instantaneous speed. All right, but we don't. We are not going to determine that instantaneous speed of the 4 kilogram mass when it reaches that point. Okay, the problem doesn't require us to find that out. Okay, but you have to realize that both the 12 kilogram mass and the 4 kilogram mass will have their own kinetic energy. All right, and the total kinetic energy is what is represented by this term in the equation: 1/2 times the mass of the system. All right, mass of the system multiplied by V2. Okay, what does that mean? V2 is the speed of the of each, all right, of each mass, both the 12 kilogram as well as the 4 kilogram, but at different points. All right, at different points, two bodies can have the same kinetic energy. All right, even if the potential energy, okay, may not be the same. All right, because for the 12 kilogram, upon reaching or about to reach point B, we said its potential energy is 0. But at the same time, that of the 4 kilogram mass, since it has acquired a certain vertical distance, will also have its own potential energy. All right, and that is here represented by m2gy. I hope you understand why our equation uh, for the conservation of mechanical energy is expressed like this. Because not all situations will have the same way of representing the kinetic and the potential energies at the start and at the end. All right, this is only applicable in this situation. Now, since we're looking for V2, all right, V2 can just be isolated like this. All right, unlike in the previous problem where we see mass in the left side of the equation, then on the right side there's also the symbol for masses. But unfortunately, these masses are not the same. Okay, that's why the label doesn't have a common subscript, meaning we're talking about different masses. Okay, in each term in the equation, m1 is only for mass 12 kilogram, while m2 refers to the mass of the 4 kilogram, and m12 refers to the total masses. So, uh, okay, if you like the way the formula used in the first example or in the second example, where the masses was, you're able to cancel the mass, so that makes our solution quite easy. This time around, we can do that. All right. So still the mass m1, m2, and the total mass are in our equation or in our working formula. But that's not hard because all you have to do is substitute the two masses. All right. So this is what we are going to do in getting the answer, and that will be shown in the next slide. So this is how we are going to calculate for the final speed of the system, V2 or V, no subscript because that applies for both mass M1 and mass M2. All right, and this is our working equation. B squared is equal to 2gy multiplied by the difference between M1 and M2. And all of this will be divided by the total mass, meaning M1 plus M2. So substituting the given, we get this result. All right, and further simplification will arrive at the value of the final speed, which is equal to 4.4 meters per second. All right, so we are done actually in answering our question number 3. That is the uh, speed of the system that we wanted. Okay, but just to show to you that using Newton's laws of motion, all right, can still be applied, or was actually applied, no? When you probably when you were discussing application of Newton's three laws of motion, and here we will do it, okay, just to convince you that, as a matter of fact, the Newton's second law as well as the third law are actually the basis, okay, for having this equation for the principle of mechanical energy being conserved. All right, but that's quite a long story. How we came up with the equations for conservation of mechanical energy, which was actually based on Newton's laws of motion. Okay, so this is how we do it using Newton's second law. All right, just like in the first method using the conservation of energy, we also treat the two buckets as a system. All right, we call it the bucket system. And uh, what we do here is look at where the what do you call this? Where the forces are acting. What are they? Okay, and how are they directed? Okay, so we want to know what is the net force acting on the system. So let's look at the diagram again as a system. All right, we can say that the force of gravity, uh, the force of gravity of what you call this, the 12 kilogram, meaning its weight, is pulling this down. All right. So as it's being pulled down, there is an opposing force, of course, and that opposing force comes from the weight of the other mass, the 4 kilogram mass. So when treated as a system, we can imagine only two forces, okay, opposing each other. The weight of the 12 kilogram being directed down, and then the force of the 4 kilogram mass, okay, which contradicts or opposes, okay, uh, the direction of the 12. In other words, okay, when we are going to convert this 12 kilogram into its equivalent weight in Newton, what we get is 117.6 newtons. All right. And then the other force acting on the system is that of the 4 kilogram mass, which, when multiplied by acceleration due to gravity, will give us 39.2 newtons. All right. So this constitutes our net force acting on the system. All right. This is F net. Now, we equate this to m times a. Remember, Newton's second law, F net equals mass times acceleration. But the mass here is already the mass of the system, and that is 12 kilograms plus 4 kilograms, multiplied by their common acceleration, represented by a, of course, and then you will see that only acceleration here is unknown. So we can isolate that and come up with this working equation for the acceleration, 78.4, which is the net force, divide that by 16.0 kilograms, that's 78.4 newtons, and we will get the acceleration of 4.9 meters per second squared. All right? This acceleration is the acceleration of each mass. So imagine from rest, the 12 kilogram is accelerating downward. All right? Downward. And then when it reaches about to reach point B, its final speed, okay, its final speed will have, I mean, when it has a final speed, it also has a final kinetic energy. All right. So that was mentioned earlier. We are on Newton's laws of motion. So this equation, I mean this acceleration, is what we are going to use to determine the speed final of the 12 kilogram mass. And that's essentially, or basically, applying what we know in kinematics. There's that formula in determining the final speed of a body, all right, when it starts from rest, and then it travels a given distance, okay? The original formula is actually v final squared is equal to v initial squared plus 2 times the acceleration multiplied by the distance traveled. All right, as applied here, since there is no initial speed, all right, the 12 kilograms started from rest, therefore v1 is already cancelled, and we are only left with this working formula for the final speed, square root of 2 times the acceleration times the displacement or the distance traveled in reference to our chosen, okay, reference level, which is at point B. So what we get here, just substitute 2 times 4.9, the acceleration we got earlier, multiplied by 2, and then finally, getting the square root of the product, we get 4.4 meters per second. And that confirms our first answer for the final speed. All right. So both methods, okay, the principle of conservation of mechanical energy and applying Newton's second law of motion will help us out in determining what we want to calculate, such as the final speed of a body. All right. So it's up to you now. All right. Which one method you think is better or more effective? Okay. One method which you think you won't be able to, what I mean is you won't be able to make any mistake. All right. So is it the conservation of energy method or the original principle behind the conservation law, which is Newton's three laws of motion? All right. So that ends our tutorial for this video. Thank you very much. Thank you very much for watching. Don't forget to subscribe.